show that the real surface of which is the equations E upon L equals to F upon M equals to G upon M holds either in a plane or a spherical. Solution: since L equals to minus n1 dot r1, M equals to minus n1 dot r2 equals to minus n2 dot r1, n equals to minus n2 dot r2, let E upon L equals to F upon M equals to G upon M equals to 1 upon K. So L equals to E into K, M equals to F into K, and N equals to G into K. Since L equals to minus n1 dot r1, which implies L plus n1 dot r1 equals to 0, which implies E plus n1 dot r1 equals to 0, which implies K into r1 dot r1 plus n1 dot r1 equals to 0, because E equals to r1 dot r1. So which implies K r1 dot r1, K into r1 dot r1 plus n1 dot r1 equals to 0, which implies K into r1 plus n1 dot r1 equals to 0. Similarly, from the relation M equals to minus n2 dot r1 equals to minus n1 dot r2, n equals to minus n2 dot r2, and M equals to fk and n equals to gk, we get K into r2 plus n2 dot r1 equals to 0, K into r1 plus n1 dot r2 equals to 0, and K into r2 plus n2 dot r2 equals to 0. Since n1 and n2 both are the perpendicular to n, therefore each of them lies in a plane of r1 and r2. Therefore K into r1 plus n1 and K into r2 plus n2 lie in the plane of r1 and r2. Since r1 not equals to 0 and r2 not equals to 0, and the vector K into r1 plus n1 is not a perpendicular to the both r1 and r2, therefore the equations K into r1 plus n1 dot r1 equals to 0 and K into r1 plus n1 dot r2 equals to 0 will hold only if K into r1 plus n1 equals to 0, which implies n1 equals to minus K into r1, equation 1. Similarly, from the equation K into r2 plus n2 dot r1 equals to 0 and K into r2 plus n2 dot r2 equals to 0, we have K into r2 plus n2 equals to 0, which implies n2 equals to minus K r2, equation 2. Differentiating 1 with respect to V and 2 with respect to U, we get n12 equals to K into r12 minus K2 into r1, and n21 equals to minus K r21 minus K1 into r2, but n12 equals to n21 and r12 equals to r21. So we have n12 plus K into r12 plus K2 into r1 equals to 0, n12 plus K into r12 plus K1 into r2 equals to 0, minus subtracting equals to this term from this term cancel out, so this is equal to K2 r1 minus K1 r2 equals to 0. or K2 R1 K2 into R1 equals to K1 R2 equation 3. Since R1 is not parallel to R2, therefore 3 will holds K1 equals to 0 and K2 equals to 0. So K is independent of both U and V. Thus K is constant. Now from 1 we get N1 equals to minus K R1, or R1 equals to minus 1 upon K N1. Integrating we get R1 equals to 1 upon minus 1 upon K into N1 plus A, where A is a constant of integration, or R1 minus A equals to minus 1 upon K into N. Squaring we get R minus A whole square equals to 1 upon K square into N square, or R minus A whole square equals to 1 upon K square, because N square equals to 1, which shows that the locus of R1 is a sphere, hence the surface is a spherical. Again, if K equals to 0, we get from 1 and 2 we get N1 equals to 0 and N2 equals to 0, which shows that N is a constant, that is, it is independent of the both U and V. Thus N is a constant vector at every point of the surface, hence the surface is plane surface.